Hello and welcome. In this video, we're going to be talking about gram atomic mass and molar mass. The reason that we're going to talk about these things is because eventually in chemistry, you're going to get to a concept referred to as stoichiometry. And in stoichiometry, you're going to need to be able to talk about the mass of elements and compounds, whether it is a covalently bonded molecule or an ionically bonded formula unit. And when you take those values, they need to be values that are actually useful when you go into the lab. So as a result, you will end up talking about either the gram atomic mass or the molar mass of a substance. So let's start out and talk about the definition of gram atomic mass, something that's also referred to as the GMA or GAM. This is the mass of an element given in grams per mole. Now, probably familiar with the idea of grams, but this concept of moles you may not have heard about before. So let's delve a little bit deeper into that first. The idea is this: the mass of an individual atom is so incredibly small that a measurement in grams is actually not even useful. If you take a look at the lightest atom that we have, hydrogen, that is just one proton and one electron, the most abundant type of hydrogen that there is, a single atom of that hydrogen has a mass in grams that's 1.68 times 10 to the negative 24th grams. There's not even a balance in the world that is sensitive enough to be able to give us the mass of a single atom of hydrogen. So as a result, because the mass of individual atoms is so incredibly small, we use what's called the atomic mass unit, or the AMU. You can also hear this referred to as the Dalton, in honor of John Dalton, who originated the atomic theory. Here's a problem though. AMUs, they're not useful either. We can't go into a lab and pull out a balance and mass out compounds in terms of AMUs. Our balances in lab, they mass in either grams or they mass in kilograms, not AMUs. So for a solution, we use an equivalent mass in grams. The idea is that when you have the atomic mass of an element in terms of grams, that mass is equivalent to the mass of a single atom of that element when given in AMUs. So if we take a look at the periodic table, right, then you can see on this periodic table, if I zoom in just a little bit, that I have what's referred to as the relative atomic mass. The reason it's relative is that there's no units on this. So if I'm looking at hydrogen, the simplest element that we have, it has a relative atomic mass of 1.008. Well, if I'm talking about the mass of a single atom of hydrogen, then that's 1.008 AMUs, which again is not useful in lab. But what we can do is take an equivalent mass in terms of grams, and we can use that. So therefore, its gram atomic mass would be 1.008 grams, but that would be per mole. So now the question becomes, what do we mean per mole? Well, to answer that, we have to look at how many individual atoms of a specific element it takes to give us an equivalent mass in terms of grams. That's the question that we're really wanting to answer. So if we take a look at one atom of hydrogen, it has a mass of, again, that 1.008, what's typically rounded to 1.01 AMUs. We want to know how many atoms of hydrogen, each with a mass of 1.01 AMUs, that it would take to give us a cumulative mass of 1.01 grams. So here's the way that we think about this. If you've ever seen a double balance, picture one now. Okay? On one side, we're going to put a 1 gram mass. On the other side is where we're going to place atoms of hydrogen, each with a mass of 1 AMU. And we're going to look to see how many atoms of hydrogen it takes to give us a mass that's equivalent to 1 gram. So I put my 1 gram mass on, the balance shifts. I then take my first atom of hydrogen with a mass of approximately 1 AMU and put it on there, and not much happens. So I take a second atom of hydrogen with a mass of 1 AMU, put it on that balance. Now I've got 2 atoms of hydrogen, each with a mass of 1 AMU, for a total combined mass of 2 AMUs. Still not a whole lot of change. So I take a third atom, a fourth, a fifth, a sixth, and I keep adding on atoms of hydrogen, each with a mass of approximately 1 AMU, until eventually I've added enough atoms of hydrogen to give me a mass that's equivalent to that 1 gram. Then we count up how many atoms it takes. Well, we find that it takes 6.02 times 10 to the 23rd individual atoms of hydrogen, each with that mass of 1.01 AMUs, to give me a cumulative mass of 1.01 grams. That's 6.02 times 10 to the 23rd. That is referred to as 1 mole. And we can do this with every element there is on the periodic table. So for example, if we look at helium, a single atom of helium has a mass of 4 AMUs, and we want to know how many atoms of helium it takes, each with a mass of 4 AMUs, to give me a cumulative mass of that 4 grams. So again, our double balance. But now on one side we're going to put a 4 gram mass, and on the other side we're going to put our atoms of helium. So I put that 4 gram mass on, the balance shifts. Then my first atom of helium, 4 AMUs. Then my second atom of helium, so a total now of 8 AMUs, because each helium would have a mass of 4 AMUs. Then my third, so a total mass of 3 AMUs, and then my fourth, fifth, sixth, and I keep adding and adding helium atoms until eventually I've added enough helium atoms that their combined mass is equivalent to 4 grams. Then we count up how many helium atoms it takes. Turns out it takes that same amount, 6.02 times 10 to the 23rd individual atoms of helium, each again with that mass of 4 AMUs, to get the cumulative mass of 4 grams. So in chemistry, we refer to that amount, 6.02 times 10 to the 23rd, as being 1 mole. And the idea is if you have 6.02 times 10 to the 23rd particles, you have 1 mole of particles. And that value works very much like the dozen. Instead of always having to say I have 12 eggs or 12 pencils or 12 roses, we can say we've got a dozen. And the same thing works with this value of 6.02 times 10 to the 23rd. If I have that many particles, then I have 1 mole. Okay? That value is also referred to as Avogadro's number. And taken out of scientific notation, it's 602 sextillion. So an extremely large number of atoms to give me a mass that is equivalent in terms of grams. So what we can do is rewrite kind of a definition to the understanding that for any element on the periodic table, it's going to take 6.02 times 10 to the 23rd, or 1 mole of atoms, to get a mass in grams that's equivalent to the mass of an individual atom in terms of AMUs. And that term particle that I threw out there just a moment ago, that can mean atoms, ions, molecules, or formula units. So the idea becomes this. If you want to find the gram atomic mass of an element, you simply look it up on the periodic table. You look up its atomic mass, and then the gram atomic mass will have the exact same numerical value, but in terms of grams per mole. So if we look back at this periodic table again, if I'm looking at hydrogen and it has a mass of 1.008 AMUs, that is talking about a single atom, or 1 atom of hydrogen. But if I put the units of grams onto that value, now I'm talking about 1 mole of atoms. So we can look at, say, beryllium. It has an atomic mass of 9.0122. If I put the units of AMUs, that is going to be per atom. But if I write it as 9.0122 grams, then that is automatically per 1 mole. And this would be your gram atomic mass. Same numerical value as what we find on the periodic table, but in terms of grams per mole rather than AMU per atom. So with that idea, we now can branch into three other definitions that we have. We have what is also referred to as gram molecular mass, and this is simply the mass of a molecule given in terms of grams per mole, where a molecule is a compound that is covalently bonded. The second term that we've got is what's called gram formula mass, and this is the mass of a formula unit given in terms of grams per mole. A formula unit is nothing more than a compound that is ionically bonded. Then we have what is typically used, and that is called molar mass, the mass of a compound, regardless of whether it's ionically or covalently bonded. And that mass is given, again, in grams of terms of grams per mole. And what we find in chemistry, what you'll find in chemistry, is that molar mass is the term that's most often used when referring to the mass of elements as well as compounds. Technically speaking, if we're looking at the mass of a single type of element, we should really use gram atomic mass, but you'll find a lot of teachers and a lot of professors going on and referring to it as the molar mass. Okay? So just be aware of that. So hopefully all of this has made sense. If not, feel free to leave a comment and I'll get back to you as soon as possible. Thanks. Take care.